Hey guys, this is Tim from PhysHow with another exam tutorial. This time we're going to be looking at quantum well or particle in a box problems. And this video is really going to be for people who have mastered the basics of this. You know the Schrödinger equation and its solutions, and you want to move on to something a bit more advanced. So things that you might see in an exam. So if that's what level you're at, then great, keep watching. If not, maybe go do a little research first. So as usual, I recommend that you pause the video and take a quick read through the question to familiarise yourself with what we're doing, and maybe even try it yourself. You'll probably get more out of it if you do. And then once you're ready, you can restart and we can walk through the question together. Now with that said, let's go ahead and jump into our question. So we're starting from 1a and let's see what we've got here. Our question tells us, contained within a potential well, shown in figure 1, so that's down here, is a particle of mass m and energy E. Simple stuff, right? Sketch the particle's wave function for E greater than u0. So let's take a look at what that means. In my window on the left, I have the same picture. So this is region A here, and this is region B. And what do we want? We want to sketch the particle with E greater than u0. So that means our particle is going to be above this potential energy u0 here. So it's going to be somewhere in this area, which means that there's no exponential decay, there's no tunneling happening here. So let's see what that looks like. We start off with just a simple wave function here, and then we move to this step, this energy step, where our well goes from a depth of E to a depth of E minus u0. So what happens here is our particle loses some energy, and when that happens, its wavelength is going to get longer, so it's going to look something like this. So we start from a quite short period here, a relatively short period, onto a longer one, because we have this lowering of energy here, and that's just because the particle's energy, total energy, is E, so this is the energy of the particle, equals E0, so this is some constant base energy, minus V. So this is minus the potential of the well. So you can see once your potential of the well goes up, the energy of the particle goes down. So that's all we're doing here. And what's important to note is that I haven't drawn anything specific on here. I haven't given this some relative length. I've just made sure that it's clear that this wavelength here is longer than our beginning wavelength in region A. That's all you need to worry about. So that's our question A. That was really easy, right? 3 marks. And question B is very similar. Sketch the particle's wave function for E less than u0. Okay, so that means we're down here in this area. So what does that look like? We have, again, some wave function here, which is going to come up here. This should be an even period, but I'm not great at drawing. And then we're moving into this step, and your particle isn't reflected here. It's going to tunnel through and decay, because you still have some probability of moving through here, right? So it's going to decay to some 0 point because we have infinity out here. That's what these arrows mean. I assume you guys are aware of the conventions here. These arrows mean that outside of this well, this whole area has infinite potential energy, essentially, which means that our particle can never get out of here. So we have a wave function here that's just a sum of signs, and then we have an exponential decay as it moves outside of our well into this step. And this is our wave function B. So there you go, there's A and B done, and there's 6 marks already. And really all you need to think about is just making sure that what you've done is clear. So Maybe even write down your energy relation. Your E is some constant energy minus U0 in this case, in the B region. But just make it clear that this wavelength here in your step area is much longer than your wavelength here in region A. And again, make sure that your sine wave here is obviously a sine wave and not exponential decay like this area. So that's A and B out of the way. And now let's move on to question C. So what do we have? It asks us, what are the boundary conditions the wave function faces at x equals 0, x equals L, and x equals 2L? So this question is really just a case of memory, right? You just have to think about what you know about particles in boxes. So at x equals 0, our boundary conditions are that our wave function psi, so this is our wave function, so it's at a boundary and it's at an infinite boundary and it's being fully reflected, and at reflection you know that this has to equal 0. It has to hit a 0 and then bounce back. So x equals 0, which is this wall, it's going to be reflected, and your wave function psi of x also equals 0. And that's the only boundary condition there, that's all you need to worry about. What do we have next? X equals L. So let's write that down, x equals L. Now x equals L is at this step in our well. So there's a transition happening here, so we're going from one regime to another. In this case our wavelength is lengthening here, and in this case we're moving from a sum of sines to an exponential decay. And you can sort of tell from looking at the picture what's going to happen here. So let's go ahead and write down our psi of x. Here, this is our wave function again. And the first thing is that our wave functions join up. There's no break here. So our wave functions have to be continuous. They have to meet at this transition point. So let's just write down cont. So our wave functions are continuous. And the second thing is that our wave functions are smooth. So there's no jagged changes here. Our wave function isn't sort of going like this. It's a smooth line between them. And what this means is that the derivative of the wave function, d psi by dx, also has to be continuous. Right? Because our d psi by dx tells us about how our wave function is changing in time, and a break in our d psi by dx means a sharp change in our wave function. So at a transition, at a step, the function itself is continuous and the derivative is continuous. And finally, let's see what happens at x equals 2L. Let's go ahead and write this down. And x equals 2L again is an infinite barrier, and it's just the same thing as x equals 0 basically, which means that psi of x equals 0 at x equals 2L. And these are the boundary conditions, and you can get these from inspecting the picture really. It's not so obvious at the edges, but all you have to remember is that your particle is being fully reflected, and it has to be reflected at a node, so it must be 0. And you can see from the picture quite easily that your wave function is continuous and it's smooth, so you get these conditions for L. And that's another 5 marks picked up. So let's move down to D. And it gives us some definitions for K, and this is actually a kappa, so this isn't the same as our K. So this K applies when our particle is in region A, because there's no U0 barrier here, there's no step. And the kappa applies in region B, because then we change our particle's energy quantization to have this U0 factor here, because we're dealing with a step. And what does it want? Write down the most general solution to the Schrödinger equations for a particle of energy E less than U0 in both region A and region B of the potential well. Okay, so again you can sort of get this from the picture that we drew earlier, or you can get it from memory. Let's look at the picture real quick. So it wants E less than U0, so we're down here in this B regime. And first of all, it wants the general solution of the Schrödinger equations for region A. So this is just, it looks like a sine wave, right? So our wave function, psi of x, has the form A sine, and we're in this region A, so we're dealing with k. So A sine k of x plus B sine, B cos, sorry, k of x. And A and B are some constants that we don't know, so you can scale your sine and cos accordingly, and we'll find these out later. And so this is in region A. So let's go ahead and call this psi A. And it also wants region B, so let's put our psi B here. And here our wave function isn't a sum of sines, it's an exponential decay. So we have another arbitrary constant here, c, times an exponential e, and this is kappa now. So when I do a curly k here, this means kappa. I don't know how to better draw this for you. It's going to get confusing, I think. But anyway, we have some constant, c, e to the kappa x, plus some constant d, e to the kappa x. In this case it's minus, so we have an exponential growth and an exponential decay, and it's kind of obvious that we have this term here dominated by an exponential decay, but we can't just cancel out our growth just yet. We have to do this formally, and maybe you'll see something surprising when we do. So that's all we need for question D. That's 5 marks, and really all you need to remember is that K is our region A because we're not modifying our energy here, and kappa is the region B because we are modifying our energy to take into account this step, this U0. So just remember where to use these things. So now we're moving on to the final part of our question, E. And we've had kind of an easy ride here. I've rushed through these questions a little bit. I've neglected to mention some stuff that's maybe kind of important, like the definitions of the Ks and kappas, but I think you guys know what those are, the quantization of energy there. But now we're reaching the final part, and this is really the meat of the question. This is where you've got to think and not just regurgitate things that you've seen before in books or in lectures or whatever. So it wants us to show that the following must be true. I'm going to write this out a little bit bigger so you guys can see, because maybe it's too small there. So this wants us to show that K over kappa is equal to tan K L, and then a bunch of exponentials up here. So e to the minus, and these are all kappas, kappa L, apologise for my writing there, but this is what we're trying to prove. The terms in this, we should be able to see that it looks quite familiar. So we've got our k and our kappa here, and we've got all our exponentials, and this is a tan, which is just sine over cos. So this looks a lot like our definitions up here for our Schrödinger equation solutions, just sort of stuck together. So it seems like that's a good place to start with our Schrödinger, our psi A and our psi B. So this looks a bit daunting at first, but it's made up of things that we already have up here from question D. It's made up of our psi A and psi B. And we know that this is going to be the culmination of this question. So it's going to use things that we already know from our questions before. So let's start working on our psi A and psi B. Let me move this page up a little bit further so we remember what we're looking at. these are our boundary conditions. And let's just plug those in and see what we get. So let's start with psi A. So this is psi in region A, our wave function in region A. And we'll start by putting in the boundary condition of x equals 0. So this is psi of 0. And we know that this is equal to 0. And this is also equal to a sine k, and now our x is 0, so it's k of 0, k times 0, plus b cos k times 0. So if we just work out our coses and sines, we get sine of 0 here, which is just 0, so we get 0 plus, and we have cos of 0, which is 1, so we have 0 plus b. So what that means is that we want this whole thing to equal 0, so this b must equal 0. So we've already eliminated our cos term here because this whole term now is 0 because of our b being 0. So we know that psi a is just a sine kx. So that's part of it done. And that's all we can do with our x equals 0. So let's move on to x equals L. So what do we know about x equals L? So we know that at x equals L, psi of x has to be continuous. So what that means is that as we move from region A to region B, there has to be no break here. So if we write that down, it just means that psi A of L is equal to psi B of L. So let's just put in our psi A and our psi B, which are from question D, and we get A sine k L from psi A, and we know that b cos, this b cos term is all equal to 0, so we'll forget that. And this is equal to psi b of L, which is c e kappa, remember, not k, kappa, L, plus d e to the minus kappa L. My kappas are getting worse and worse, but hopefully you can keep up. So we know that this is continuous. And further to that, we know that the derivative of both of these terms has to be continuous. So let's move down here. So we know that the derivative of psi A at L is equal to the derivative of psi B at L. So let's go ahead and differentiate this. So if we differentiate our psi A, we get k from our sine times A, and now it's a cos k, and this is evaluated at L, so this is cos k L. So this is the derivative of our psi A, and now let's do the derivative of our psi B. And if we do that, we just take out our kappa, because it's an exponential, and then we have our c again, e kappa L, and this time it's minus because we take out the minus from our exponential, and again we've got a kappa, and we have d e to the minus kappa L. So these look like simultaneous equations to me, and let me just make some space here. Go back to my brush, and this is my equation 1, this is equation 2. And what we're going to do here is we're going to divide one of these equations by the other, because we're aiming for a tan and we've got a sine and a cos here, so they obviously need to be divided. And it's not immediately obvious which one should be divided by which, but I'm just going to go ahead and tell you that in this case 2 should be divided by 1, if you did it the other way around, you would get the same answer, but you would require a little bit more manipulation of your algebra along the way. So let's go ahead and write this down. So we've got 2 divided by 1, and I'm going to rush through this, but hopefully you can see that our a's cancel here, and we get to a tan from sine over cos. Let's start with the left hand side. So we have k, our a's cancel because there's an a on top and bottom, and we have k cos kl over sine kl. So that's our left hand side done, and now I'll do the right hand side, and we get kappa c e kappa l minus kappa d e to the minus kappa l over our equation 1, right hand side, which is just c e kappa l plus d e to the minus kappa l. So this is our equation, and it's starting to look a bit like what we've got in the question, and now we can just move things around. So we have, this is 1 over tan here, which we can move to our right hand side, and our kappa can come over to our left. So what we get is k over kappa is equal to, and then we move our sine and our cos to the right hand side, and it becomes a tan kl, and then we're just multiplying by all of our, this is c e to the kappa l, because we've taken our kappa away to the left hand side, minus d e to the minus kappa l over c e kappa l plus d e to the minus kappa l. And this looks a lot like what we need for our final answer, but we just have these c's and d's lying around, and our exponential powers aren't quite correct. So let's look at our final boundary condition. Let's go back up, and we know that at x equals 2l, psi of x equals 0. So let's move down here, and I'll write this out again. X equals 2l, psi of x equals 0. So this is our boundary condition, and this is our final boundary condition. So let's plug this in. So we have our psi of ce to the kappa x plus de to the minus kappa x. This is psi b. So let me just go ahead and copy this down. So we remember what we're dealing with. And I've chopped a bit off, but it doesn't matter. You guys understand, I think. So, at x equals 2l, psi of x equals 0. So what that means is ce to the kappa x, and then we insert our 2l here, plus de to the minus kappa 2l, so we've replaced our x's with 2l's now, equals 0. This is our boundary condition. And again, I'm going to rush through this, but basically what we're going to do is try and isolate this d, so we can replace it with something else further up. So what we get is d equals minus c, so we subtracted our c term over here, and this is going to be e to the 4 kappa l. See, we just divided through by our e from our d here. So this is what we're using for d now. And we're just going to go ahead and sub this into our term here, our k over kappa. So let's write that down, k over kappa equals tan KL. And I'll write this out in full because it gets a bit messy. So we have C e to the kappa L. And now we're replacing our d up here with our c. So we have minus times a minus is a plus. C e to the 4 kappa L multiplied by e to the minus kappa L. And then on the bottom we're going to do the same thing. So we have our initial c e to the kappa L term. And then we'll replace our d by our c e to the 4 kappa L. So this is minus times a plus becomes a minus. And we have our c e to the 4 kappa L multiplied by e to the minus kappa L, just like above. And now all of our c's cancel because we've got c's on every term, top and bottom. And if we multiply these together, we get that this is equal to tan KL e to the kappa L plus e, so we get our exponentials up here, we just get 4 kappa L minus kappa L, so this is 3 kappa L, and then on the bottom we have much the same thing, so e to the kappa L minus e to the 3 kappa L. And that's almost what the question is asking for, but there's a bit of trickery here. So instead of this kappa L and 3 kappa L, it wants minus kappa L and kappa L as our exponential terms. So all we're going to do is just multiply this top and bottom by e to the minus 2 kappa L. So you're essentially multiplying this whole thing by 1, right? Because this is just a term divided by the same term again, which is equal to 1. You're not changing this in any way, you're just changing the way it looks. So if we do that, we end up finally with k over kappa is equal to tan KL e to the minus kappa L plus e to the kappa L. And you should be seeing that this looks pretty familiar now. E to the minus kappa L minus e to the kappa L. And this is what the question asks for. So that wasn't too hard, it was just a lot of maths really, and comparing boundary conditions. What I would say is we start off with a very simple question asking us, show that the following must be true, and then this quite complicated term here. And to first look at this, it's difficult to see where it comes from, but it's the end of the question, it's worth a lot of marks, so you've got to think that the examiner is expecting you to go back through the question and use what you've answered previously, especially because the rest of this question was so simple. So always go back and look at what you can apply to your final question, your crescendo. And don't worry if you get the wrong sort of answer out. So for instance, if you finish the question and you got stuck around here with your e to the kappa L and e to the 3 kappa L, you've done everything. The last bit is just maths. You know the physics, you obviously know the physics going on here, so don't worry about it. You'll still get most of the marks. You maybe lose 1 mark, half a mark. And again, don't worry too much about the drawing. Obviously it helps if you can see what's happening, but something like this would be fine. This would be full marks, because you would just get a mark for... So this is 1 mark for having a short wavelength here, another mark for having a long wavelength, and a mark for having these end at 0. That's all. That's 3 marks. You don't have to write anything, you don't have to draw some Picasso-esque piece of artwork. So that's the end of the question, and I hope you found this video helpful, and I'll see you next time.